Thank
Okay.
you. Okay,
Our
so let me,
okay.
oh,
Our next speaker is Eva Silverstein, and she's gonna tell us about BI for AI.
thank you very much. And let me, as the last speaker, let me give my big thanks to the organizers on behalf of, I think, all of us for a wonderful meeting. I don't think we should worry so much about the virtual format. It's been very interesting. I've enjoyed every single talk. So I'm going to talk about a project that's been going on for many epochs. It really started in interesting discussions initiated by Dan Roberts and friends on a connection between inflationary dynamics and optimization. And what we'll show is that a sort of form of early universe inflation inspires a version of optimization, which is really very different from any of the standard ones. It's in a nutshell, it has no friction, and yet it stops at the bottom of the loss for reasons to do with the fact that the relativistic speed limit of the dynamics is the loss function itself. So the physicists in the crowd can probably derive the whole thing from what I just said, although it involves some more ingredients that I will need to explain. So this is largely in collaboration with Bruno De Luca, as well as George Panagopoulos, who already went off to industry, and our machine overlord collaborator, which in this case is a certain ResNet for some of the experiments. And we hope it'll appear early next year. Okay, so as you guys all know, for many applications, not just in machine learning, but including that, one wants to minimize or at least descend a long way along some objective function. It can be non-convex or it can have shallow valleys. There are many possibilities. And the hope is to have an optimization scheme that's robust and can solve that problem as robustly and as generally as possible. There are many versions of that. For some of our experiments, we'll focus on something we have a great deal of control over, and which also is relevant for the kind of string data connection, which is solving PDEs. Of course, PDEs occur all over science, not just in our in the HepTH field. And for that, we'll just take a loss for which you really want to get to zero as the global minimum, which is the sum over points and equations of the squares of the equations in the boundary conditions. Okay, so that's one example. We'll also show that it works for the standard machine learning data sets like CFAR. Of course, this is a very successful field. Gradient descent methods and their various variants, of which there are many at this point, can work quite well. But people don't really understand them, how they work, how to predict how well they'll work. And so they can, though they don't need to, but they can get stuck at an undesired local minimum or saddle point. They need not sample all of the solutions. So for solving PDEs, you really want to get as much information about not just one, but all the solutions. So the idea here, as I mentioned already, is to take some inspiration from our field in a different way. So from early universe cosmology, we have a lot of understanding of various ways it could work to descend a complicated landscape. So here we'll take inspiration from DBI inflation, where you have a relativistic speed limit that depends on the field value itself. And in particular here, we will take the speed limit to be the loss V, and it need not have any friction, just no friction per se. And because of that, it will satisfy energy conservation. And yet it stops where you want it to, at least for this sort of problem, and also any kind of least squares loss problem. We noticed a paper in the literature already that uses relativity, although they don't have the aspect that's so crucial here of the speed limit actually being tied to the loss. However, it's a very interesting paper, which they call relativistic gradient descent. Although in our understanding, they kind of undervalued SGD in some of their tests in comparing to that. Okay, so for us, I already sort of said this, we've had a ton of talks on this general type of subject, many of them using the special features of Calabi-Yau manifolds. We also had work doing similar things for the case of hyperbolic compactification, where we know the metric, but the other fields are important. It's a general question, and here I'm just setting the stage by reminding us how it works. with a neural net, output being essentially playing the role of the ansatz for solving the the PDEs or the data science problem, depending on your application. But for PDE solving, I already said, let's just take this most simple-minded form of the loss function and descend it, and we'll talk about this new optimization protocol that is quite distinct from gradient descent. So you might ask why we're doing this, given that what early universe inflation requires, first and foremost, is a nearly constant potential V, and yet we want to go to the bottom of ours in this field, right? But just bear with me and we'll see why it's relevant. I essentially already said it. Okay, so in this context, there are basically two classes of inflationary mechanisms. And the happy thing in terms of strings and real data is that these things can be distinguished. We according to at least the number of modes we get in observations of the universe. It hasn't quite happened yet, but one hopes for full testability using large scale structure, for example. Anyway, these two kinds of inflation, the most traditional one is called slow roll, where you have nearly constant potential because of the potential being rather flat and Hubble friction slowing the field down. But the other option is when interactions slow the field down, and that's where this type of model enters. And in it, the novelty involved the fact that the speed limit in relativity was not just a constant, but it depended on the field. And again, for our purpose, we will take that to be the loss. But for now, let me just review that already in this subject, these two options are just distinct. They are really, really different in terms of both the mechanism for in this case, the early universe physics, the inflationary physics, and also in their observables. So they just are distinguishable based on actual observations. And that's sort of the thing to start with here, is that if we make an optimizer based on that, it's gonna, whatever else is true, it's gonna be quite distinct from gradient descent. And so we're going to work out what that implies. And it does imply some positive, some favorable features. So we'll do, as usual in this beautiful field, we'll do some theory and some experiment to test that theory. Oops, okay. So, but we don't need the friction. The Hubble friction that is involved in inflation is in this type of model is not relevant. And so we can work with the, well, in that context, the very inside horizon physics, the without any gravity. So that just boils it down to a dynamical Hamiltonian system with this action. Whereas I keep saying the speed limit in parameter space, which we call theta, is given by the loss, which we call V of theta. And we can work in a canonical formalism with our conjugate momentum pi and express things in either way. The thing that's an extra handle on our optimizer, given all that we've said, is that there's no explicit time dependence here. So there's conserved energy. And that would not be true with a friction term. Okay, so we can immediately come to some conclusions. It's just mathematically impossible for this dynamics to stop at a local minimum because the energy being constant doesn't allow that. It also cannot overshoot V equals 0. It just has to stop there because of the speed limit. We'll get into the ways that this can fail, which has to do with the fact that, energy conserving or not, Hamiltonian dynamics can get stuck in orbit. And to address that, we'll get into really fun stuff involving chaotic dynamics, where we can introduce elements if the problem isn't chaotic enough and has such periodic orbits that the system gets stuck at. We can add elements inspired by billiards problems to get it out of orbit, to make sure that the mixing time of this system is sufficiently short and that it behaves chaotically, thereby avoiding this failure mode that exists for this type of optimization. for now, just notice that again, it's very distinct from gradient descent. And so let's trace through what that implies. Okay. To anticipate this chaotic behavior that I'll get to, once you have that, what really dictates what happens, what the prediction is for where this goes, is the phase space volume of a given region. So if you start with some droplet initially and the system mixes, the probability for finding that droplet in some volume of phase space is proportional to the volume in phase space of that region. When we employ the energy conservation in calculating that phase space volume, it's a very fun and simple calculation. First of all, here we can integrate out you can use this energy conserving delta function to integrate out the momenta and be left with an integral over the parameter space theta, which, as you can see, has a divergent behavior as you get to zero loss. So we regulate everything in this problem, so it doesn't literally go off to infinity, but it clearly dominates. Okay, this is the, we were kind of inspired by this fun old inflation mechanism. It's really not tied to that particularly. It's just a feature of any energy conserving frictionless dynamics. You can make, instead of a square root, you can have a log. There's even an inflation mechanism that accomplishes that. You can do something simpler, which is just have a two derivative action, but where the mass of the particle in physics language is inverse to the loss. So as the loss goes to zero, it gets heavier and heavier and it slows down just for that reason. Okay, so the general theme here is energy conservation. So I said that the way that this can get stuck is not to kind of contracted phase space to a local minimum or to a saddle point, but it can get into orbits and just kind of stay high on the potential. And if that happens, just as a warm up, one can add features that don't obscure the minimum you're looking for, but actually make it more chaotic and kick it out of orbit. So here's some experiments showing that in some run of this PDE, which is rich enough to be interesting. There you see an orbit, and you see when we add a particular type of feature, it gets unstuck. We'll do that in a very specific way that's, as I mentioned earlier, reminiscent of billiards problems. And shortly I'll give the algorithm. Okay, so another physicsy analogy or astrophysicsy analogy is galactic dynamics. And we all know the solar system has these long-lived orbits, but it's ultimately chaotic, ultimately unstable. In other systems, the mixing time, the instability time is much shorter. Here's a random thing taken from the internet on galactic dynamics, where you see both types of orbits, regular and chaotic trajectories. The analogy here includes the fact that there's redshifted Born-Infeld dynamics in this kind of system. Okay, so how does it work to ensure, or to go in the direction of ensuring, that one has strongly chaotic or mixing behavior, so that we get this the benefit of the prediction of the giant phase space volume in the basin of the global minimum? Well, in billiards problems, there are mathematical theorems ensuring exponential mixing in certain cases. The basic intuition is that if you take trajectories that hit a billiard ball, they disperse, just as in this picture. And if there is a mixing effect that has set in, then you get this phase space distribution given just by the volume and phase space. And just for the record, that is a stronger statement than merely ergodicity, which is an infinite time statement. Okay, so we're inspired by this. Let's just check that what mixing really means. So here's an experiment. Okay, so mixing is a real effect. And here's our algorithm. You can take the dynamics that I explained in the formulas that I had given in the continuum theory. And we can, of course, discretize that in the standard way. And that gives these equations. So that's the underlying discrete dynamics in the model. But we have various options and additions to that. We can, just by the way, for the energy, one could initialize at some high point in the potential with zero momentum or zero velocity, but we have the option of starting with some momentum. Actually, the coffee mixing thing I just showed had some initial momentum. Anyway, that's an option. Because discretization can build up errors that ruin energy conservation, we take seriously that we're engineers for this purpose, and we can just restore it. We restore energy conservation if it starts to lag behind the prediction of energy conservation, simply by small rescalings of the momentum pi. And when it comes to this business of introducing billiard-like elements in order to ensure that it mixes as quickly as it needs to, we introduce bounces inspired by billiards in two ways. One is if it's just not making progress, it'll bounce. And you can also tell it to bounce regardless of that if you want to ensure that it mixes around more than even this would ensure. For example, if you want to help it find all the solutions. Okay. So we can ask, what is the prediction for where it's going to land given not just the value of the loss at the minimum, but the shape around it, the Hessian and such. So near some minima, which are locally quadratic, let's say, you can compute the volume of the basin in phase space, and you get a particular formula for that, which is obtained in the sort of obvious way, just expanding, taking the basin to be up to where the kind of dimensionless variable reaches, the edge of the basin, where this eta in this formula is of order 1. And that gives you a definite prediction for the ratio of phase space volumes and the ratio of runs. And we check this in this is here, checking that prediction is borne out. And there's no such prediction for SGD, say. So that's the kind of handle that we have on this because of the feature of energy conservation and so on. When we consider the PDE problem I mentioned before, we find there are two solutions. This doesn't really illustrate that too clearly, but there are two solutions, and BI does find them both. Here's a table just kind of summarizing the distinctions between the types of optimizers, those traditional ones with friction, and this kind of, there's energy conservation, need for friction. So far, we focused on the issue of getting stuck or not, overshooting or not. There's also a lot of interest in the field on what's going on in sort of shallow regions, almost moduli spaces in the loss function, in the loss landscape. And actually, we find an advantage there, which we can also explain in terms of the different dynamics at late times, in terms of just the velocity in the two types of optimization. Here I've written it in the case that friction dominates. Something like this also applies on this side of the table, even if you're in an underdamped sort of regime of SGD with momentum. And in our case, we can just expand out where what the velocity looks like as we approach a minimum in a very shallow basin. And the point of this line of the table is that this is faster evolving than that. And that's what we were finding in some such test function runs. Okay.
Well, you have 5 minutes.
Is it 5 minutes, you say?
Mm-hmm.
Sounds good. Okay, good. Thank you. Okay, so let me just quickly show you some results experimentally. There are various test functions that are useful in this business that can go up to very high dimensions. I'll show you a few of those. Here's a very non-convex function. Here's 5 dimensions. We'll go to 400 in the next slide. And we do our best to help gradient descent work for this, and it does predictably do worse than BI. There's interesting work on what was called a catapult mechanism, kind of taking a large learning rate for GD, so very far from its naive continuum limit. And that, that can kind of catapult it around to get close, but then it kind of bounces out. It just seems less, so far, at least in a preliminary analysis we're doing, it seems less predictable, less robust. And again, this is predictable from the theory. In 400 dimensions, if we add some regularization, we find similar results. We do our best to hyper optimize gradient descent or momentum. It's called here, and BI gets there in a way that gradient descent doesn't. Here's the example with a shallow potential valley, which people seem to talk a lot about in these things, which also shows an advantage. We think for this reason I was explaining of the speed. I mean, gradient descent kind of slowly gets there, but that's what we're finding. You might wonder about noise, and of course we include that ultimately. So that in this kind of theoretical language, you can take ensemble averages and look at kind of stochastic behavior, but you can also think of any given trajectory as a deterministic thing with a time-dependent potential. And in physics, that would entail energy non-conservation for the usual reasons. Here, we just take the opportunity to force it on, force energy conservation on it regardless of that. And then we can conclude again that even with noise, we have these absolute statements. It can't stop at a local minimum, and it will stop at the global minimum with noise, now with mini batches included. But it is also very interesting to study ensemble averages, to look at the analog of Brownian motion in this sort of system. And there's a lot of interesting work on that subject in the field. So one paper we've been working with is that of Sho Yaeda, who did a nice discrete analysis of such things, losing no information, not making any continuum limits and so on. And we can compare, as we did above, the behavior of this type of system from the traditional ones. We can also take a careful continuum limit and look at what happens to the usual Langevin dynamics. And there are distinctions. I don't think I have time to go into it too much. But we do experiments with noise that show that it works, as we predicted from the perspective of not even taking these averages. One thing that's tentatively coming out is, in the most dumb version of Langevin dynamics, you have the random walk with a linear and time behavior. And here we have terms like that in our equations, with the right-hand side here being, the ensemble average of the velocity squared. But for us, that's bounded by V. So the way we explore the landscape is more like the deterministic version of the model in the first place. Okay, it works with noise, it works with CFAR. We made some applications to a different type of string theory problem, which involves compactifications that are quite general. Negative curvature is the most typical thing you find among manifolds, and they have very favorable properties for string compactification because they give positive potential energy, and the hyperbolic metric is known and it's rigid. The Hessian is positive in every direction, and combining that with the warp factor dynamics, you find that it's that the fiducial metric is very, very stable. And there are only a couple ingredients required to produce a de Sitter solution for the volume, and a lot of analytic handle on the analysis of the tadpole shifts away from the fiducial metric. Long story short, it's a very long story. So there's an expression for the effective potential. This is a beautiful paper by Mike Douglas. It's quite model independent. It doesn't depend on any particular choice of type of manifold that you compactify on. and it gives an effective potential that is properly defined in terms of the gauge symmetry of the problem. I bring this up both in the context of these hyperbolic things, but also as a thing to explore in terms of the idea of machine learning the landscape. So for us, we just did some warm-up example. As I said, most of our analysis that was of the de Sitter models here was analytic, with some numerical studies of important local regions in this space. So here's an example, though, of a study of the fields in a 3D warm-up example where you see a hyperbolic polygon from which these things are built and the fields that live on it. What the thing I'll leave you with on this topic, which I really didn't spell out here, is that this is a well-posed problem, including the stress energy sources that are needed for de Sitter space. These manifolds are explicit projections of a known metric space. They can be obtained as gluings of explicit sets of polygons. The group theory involved implies also the form of the Casimir energy. That's the crucial negative source in the potential energy. The flux is a global flux that's explicit, and there are parametric limits that we rely on in the analytic studies that one could compare to. For machine learning, I would comment also that we can do this thing with a PDE squared, but it's also very interesting to explore V effective itself. That's why I flashed that formula, or descend in the slow roll functionals that are variations of that expression. Again, in a way that's quite model independent overall. Okay, so let me stop here with this summary. We expect to put out a standard academic paper on this shortly, but we have more aspirations for applying it. First to scientific machine learning, like maybe large scale structure studies, protein folding, other PDEs, beyond those ones that we just used to develop the optimizer, and so on. So thanks for your attention. Let me stop for questions. I see there are lots of hands up. I didn't notice that.
Thank you, Eva. I think Gary's question was for the talk before. So Fabian?
I think Gary was, I think I wasn't the first, but I'm happy to go first if we have enough time for everybody.
Yeah.
Thank you very much. Thank you, Eva, for the very interesting talk. I have two questions. The first one, I missed this, I'm sure you explained this, but I appreciate that you cannot overshoot with your setup, but in your parameter update, of course, you're adding a final time step. So you could still sort of overshoot by going too far in the direction or not. How do you?
When it's in that region, we put an absolute value to avoid that eventuality.
So that would be something like a learning rate schedule. Your parameter updates are getting smaller.
Well, you can add that. We actually play with an option to do that. Actually, Bruno's here if you want to comment on these, where we are on those types of options, feel free. But yeah, we if it were to overshoot, the whole thing would become NaN. It would go complex, right? So
I don't mean the correction, but then once you add something, yes, then you would indeed then you would have a problem when you try to compute the next loss.
When you add something else, by something else, what do you mean? Sorry.
No, I mean you calculate the direction of your update.
Yes.
And then you actually do the update.
Right. And
when you do the update, you're adding. You have some learning rate or something that makes it sort of that updates the parameters in a certain direction. And if this is too loud, you can still overshoot. And then your next loss would be complex.
Well, we prevent that with a kind of kludge that we make it unable to do that once it's within a small deviation from zero. Once it's in that regime, just discrete or not, it's going super slowly. It's just kind of stalling there. It's like being outside a Schwarzschild black hole, and it takes forever to actually get there. So yeah, it's a good question, but we put an absolute value in there and prevent it from ever going complex.
My
And
second
then,
question-
and then if, in the event that it does something wild at that point, the restoration of energy conservation will get it back on track.
Just to make sure, so the loss cannot become complex. And what can happen is that at most is that energy will not be perfectly conserved because of this small effect. But the loss is always real. And this effect that you're talking about should be very, very small if the step size is not big.
Yeah, exactly. So the question was, how do you automatically regulate the step size? That was the question. But yeah,
yeah. So now for this version, we are not adapting the step size, so it's kept fixed. But one can think about some more refined version where you also tune the step size to avoid that. Here, you just need to make sure it's small enough that you don't have these big jumps that you're talking about. But yeah, also by itself, even without manually enforcing energy conservation, this is still pretty well conserved anyway. If the learning rate is not too big, this doesn't happen usually, at least in experiments.
Well, yeah, I mean, the thing that goes complex would be that, the square root or, the same thing written in terms of the momenta. And that is where, as Bruno says, the forcing it to go back to energy conservation restores the reality of all the quantities in the model. So it's a kludge. It's just, it's done by hand to restore that. It's a very valid question, but does that help?
Yes, thank you very much. And my second question was, often in real world applications, I mean, this is very interesting that you get just to the global minimum. And of course, if you want to learn a Calabi-Yau metric or some metric where you have a single solution, I mean, assuming more or less stabilized, there's a unique solution and you want to find it. And that's very useful in real world applications. And that's why I was interested. You talked about Cypher 10, for example. The common law has been you actually don't want to find the global minimum. You do early stopping, you stop not even at a local minimum, you just stop somewhere, and this helps with generalization. So the minimum that's picked out by your optimizer, even if it's a global minimum, it still performs very well. It's still
well, one thing you can do, I know, yeah, this is a good question. That's sort of why for this talk, at least, I focused on the case where you want to get to as low as possible. One thing that we noticed is that we can actually do early stopping in a different way. So we can add a kind of constant to the potential and stop at any value of the loss. So we can, that can just be another hyperparameter. And if the system prefers some local minimum instead of the global, this parameter adjusts it to that. So if you can do all the hyperparameter testing that you need, including this thing, you can address that case. One question we had was, is this useful for the kind of thing you just said, which is stopping early? We can stop early in a different sense. It's another good question. But long story short, this V naught can address a lot of that, we think.
Yeah, I see it's built in your system, but is the minimum, the global minimum that it finds, is this better behaved than the global minimum that's found by STD? Let's say I was just training STD to zero loss, and I was training BI to zero loss.
Well, okay, again, so let's think about it statistically for one way to answer your question is statistically. SGD will get stuck sometimes. BI cannot. It's just mathematical theorem. It cannot. So statistically, I mean, not to be hyper competitive or something, but statistically, it should do better. Like there's a reason it should. Now, in our experiments, and we really are trying to do our best to give SGD do a fair comparison, because nobody wants to waste time with a new thing if it's not useful, right? But we think we optimize its hyperparameters both, in sort of as they're given, their logs, and some of the earlier papers had, like this RGD paper claimed an advantage over SGD when in fact SGD could do perfectly well on the problem. So I'm completely with you that one should be careful about that because it already exists. It already works a lot of times. But but there's a good reason it should at least statistically fail some of the time in a way that BI can't. And in these experiments, we find that to be borne out.
I mean, my question was more about the generalization to the test
okay.
set, not
Okay.
about the absolute minimum of the loss you can achieve.
Oh, sorry. Your first question was about the generalization. I thought your second question was, how does this compare when you want to send SGD to the global minimum?
Yeah. This was the second part of my question.
Okay, so this was this. I was addressing the second question just now. Is that
okay? There are many other questions. We can maybe continue in the discussion. Thank you very much.
No, thanks.
Also
Thanks
the
a lot.
question.
It's very similar to your question, but because I think, but maybe I can say it in a way which is I think what you're also saying, which is what you're describing is the global minimum of the training set, which you may then hit perfectly, but that may not be. But you often in the real world don't know what the global minimum of all data is. So just because you stop at the global minimum of the training set doesn't mean that's the best place to be for all of the data. I think that's related to what Fabian was saying, that because you want to generalize beyond the training set, you can only look at the loss of the training set, which will then have a global minimum. And the whole point of the early stopping thing is that then you don't tie yourself and overfit.
Yes, of course. So you don't want to overfit. In the PDE problem, you want to converge to a solution that is true at every point for every equation. Okay, so you definitely want to converge to that. In other problems where you wish to do something else, what we can say is that there's this extra hyperparameter V naught. So I totally agree. This is an issue. It's a question. I would also say though that there's a lot of lore in this field, and I personally don't necessarily know what to trust of the lore. I mean, yeah.
Maybe just to say then, so you'd have an additional hyperparameter V naught, which you could then tune, which would help your generalizability, I guess. But then
if the lore is correct, that's true. Yes.
Okay. But then there's also this thing of I'm just trying to get my head also just physically around it, that if I have a data set, and you mentioned this thing with noise, where the loss is never zero, won't you then always move? I mean, it's the fact that I could sort of imagine that in some data set, I've always got some loss based on the loss function that you've defined. So then the velocity will never hit zero.
Well, so in the noise case, we think of the full batch thing as the sum of the mini batches. In the PDE, that's sum of the points at a time. But in the end, they all need to converge to zero. If you're solving a PDE, you just want to converge to zero eventually. I completely agree and understand that a data science problem would be subject to overfitting for exactly the reason you're talking about. And for that, again, our answer is, okay, you have to deal with this extra hyperparameter V naught, which, it's a totally fair question. I appreciate the question. But when it comes to noise, this is what I was saying, that from the physicsy point of view, we can think of it as, we can think about it in various ways, but one way is each trajectory is deterministic, but it involves the potential energy jumping around and so on.
Okay. Yeah, thanks a lot. That's great.
No, thank you. This is a good discussion.
Ben?
Hi. Yeah, I have a couple of small questions. So first, in terms of efficiency, if I see correctly, there's not really, it doesn't cost you very much to use these updates in comparison to standard gradient descent.
Yeah, it doesn't.
Okay.
It's similarly, it's a dynamical system, just a simple update of every step.
In terms of comparisons, you show a lot of comparison with SGD. Have you looked into comparisons with second order methods like Adam? how,
A little, yeah, sorry, go ahead.
yeah, so
we-
that's a second short question, right? Because it's
we have done some of that. We should do more. We have, we have a lot of, we're gathering a lot of statistics on such things. We could take the approach that Adam involves an adjustment of the learning rate and so on. We could add that to this, right? So perhaps the first order of business is to compare this to SGD, and then compare if there's, an advantage to changing learning rates, we could also do that on both sides of this table if you want. But I would just say, I would just leave for now, I would leave you with this to your question, which is also for Adam, it's friction based, the phase space contracts. And statistically, it will have these properties that are in direct contrast to what BI will do, and for better or worse, but it can contract to a saddle point or local minimum. Maybe you want that, maybe you don't, depending on the application. And BI can't, and even for Adam, I would say I wouldn't have an a priori prediction for how it would distribute itself over phase space. And so just because of the friction. So on the theory side, it's still in the class of frictional optimizers, but in terms of experiments, you're absolutely right. It was developed for good reasons, and it does well for those reasons. And we should do more tests with that.
And so this is also physics related somehow. That question is in terms of looking at actually, Cypher 10 or so, if you're looking at feature learning in the sense of the neural network, does it, can you see whether it learns the same features, or can you see some distinctive patterns arising? I mean, with respect to, as you were showing, the standard thing of non-Gaussianities look very different in different.
Yeah, that's a great question. I mean, yeah, it's a great question. And again, it's tied up with interesting ideas or lore in the field to do with how the landscape where you end up relates to those representations. I think it's a fascinating question.
Yeah.
Thank you.
Yeah, thanks. Looks very nice.
Hey, Daniel.
Hi, Eva. That was really
Hey,
nice
Dan.
talk.
Oh, thank you. Good to see you.
Yeah, good. Good to be here. So I have a couple of questions as well, but for the purpose of time and discussion, maybe I'll just ask one. It's sort of, it's maybe hard to have this discussion because there's a lot of lore and it's hard to respond to lore directly. I think I kind of disagree with I think some of what the previous questions asked are involve some outdated lore, but maybe just to say my question directly, my understanding is that a lot of what happens for modern deep learning systems, they're in a regime that's called over-parameterized, where there's more parameters than data, and some way of talking about that. But that means that there's really not there's many ways to fit all the training set data. There's not really local minima where things get stuck, and the question is sort of which one of the global minima do you end up with? There's like a moduli space, and I was wondering just if you had a chance to both study that empirically, and maybe there's this point about the phase space volume will tell you that you're ending up in a good place or a different place, let's say. And then also I think I was going to ask whether you considered for some maybe example potentials, some analytical solutions where you could see maybe that in this regime where there's this moduli space of global minima, where you could say something about it.
That's a great question. And actually, I think from our discussions way back in the day, you, among other people, were kind of stressing the kind of half pipe thing and near moduli spaces and so on. And indeed, sorry, let me get back to it. We have been studying that actually most recently, because maybe we kind of circled back to it a few times, but we were a little slow to realize the distinction there. The non-convex thing is easier to understand. Okay, you can get sucker, you can't. Here, it's not hard to understand either. Analytically, it has to do with what it's doing at late times in such a shape, right? So I went through this quickly, but in terms of really simple experiments, there's this example with a shallow valley, and again, we have been really doing our best for SGD to, help it, or at least, make it a fair comparison. And BI does seem to do better in this. As you say, the phase space volume along such a valley would have to do with its shape and so on. And there'd be a way to generalize the formula I gave earlier for localized minima to such a moduli space. And that's a great suggestion. This formula here gives some idea of why they're different. Though one can generalize this one to, beyond the case where friction dominates. Here I'm just writing this because it's sort of, you can immediately see why this is the formula. If you include the momentum and let that even dominate, you find a similar distinction. So I think this is something we want to, study further, because we just started really focusing on this case along with the others. So yeah, thanks. It's a great suggestion. Does that help?
Yeah, that helps. I think this may be similar to what was raised by some of the others, but there are cases where if you have a separation between test and training data, where GD would find a global, it would fit all the training data exactly, but would make different test set predictions presumably than what your algorithm does. But I think probably there are ways, for instance, in the toy model that I presented way back in my talk, that gives different answers for different training algorithms, but fully fits the training data. And you could work out, I think you could probably work out analytically what the solution would be and compare it with the GD solution. And probably it would perform, I imagine you can construct data sets for which, for one, the GD performs better, and for another, BI performs better. And maybe it's interesting. Well, maybe that's true, maybe that's not true. I don't know without knowing what the solution is, but then also maybe it's interesting to understand the features of the data, the details of the data that give you one being better versus the other. Anyway, thank you very much.
Yeah, no, that's a good notion of simplicity to use. Yeah, I enjoyed that expansion that you do. So we should combine forces. That sounds great.
Okay. I suggest we defer the remaining questions for the discussion section. And before we proceed, let's thank Eva and all the speakers of this conference for the brilliant talk, as well as the audience for the very lively discussions.